In this video, we're going to look at sketching the graph of a derivative, and so we'll know that the derivative can be represented graphically is mostly what we're dealing with here. Numerically, analytically, verbally. We'll know key features of functions and their derivatives, and they can be identified and related to their graphical, numerical, and analytical representations. And of course, again, today we're going to do mostly graphical. So if we have the graph of a function, we want to sketch the graph of a derivative. So sketching the graph of a derivative. And in a minute, we're going to take these two functions down here and sketch the graph of the derivative. Okay? When we're sketching the graph of the derivative, okay, we estimate certain values. And points of change are important. So if we have a function that goes like this, it has a little maximum here. And the graph here is increasing, and then it changes to decreasing. Well, at that maximum point, that tangent line is a horizontal tangent, which means its slope is 0. And more importantly, well, not more importantly, but equally as important, what's happening on either side, increasing and decreasing, is also going to tell us something about the derivative. Okay? So if my function f is increasing, then the derivative is going to be positive. If my function f is decreasing, my derivative is going to be negative. Now this is a two-way street. If my derivative is positive, I know my function is increasing. I can go both ways. Okay. If I have a maximum, then it's 0 is the value of the derivative, and there's a change from plus to minus because it's changing from increasing to decreasing. Now you could also have a minimum. So a minimum, something like that, also has a horizontal tangent to it at this minimum. So the derivative there is also going to equal 0. The slope is going to be 0. But it changes from negative to positive. Okay? Now we're going to get more complicated with that as we go, but for now, that is where we are and what we're going to use that information to draw our derivatives. Alright, so for the examples 1 and 2, each of these graphs is a function. We want to sketch the derivative on the graph provided here. Okay, so first of all, we always look at the change points. And we have a point here that is a local minimum. And if I extend that down to here, then this graph is going to have a 0 right there. And then there's a maximum right here. And so there will be another 0 right here. And then there's a minimum right here. So that would come down to about here. There would be a minimum. And so that would be a 0. Each one of the maxes and mins becomes a 0 on my derivative. Now technically it could be does not exist, but that's not going to apply right now. Now when I get here, if I divide this up by those change points, you can see that until it gets to this change point, this section of the graph is decreasing, and then it switches to increasing, and then to decreasing in between, and then finally it's increasing. Well, that tells me something, because if my function is decreasing, then f is decreasing, f prime is negative. So f negative, that would be down here in the negatives. Okay. It would be in the negatives until it gets to here, then it hits 0, of course. And now in between this one and this one, f prime is positive. But then it's going to switch back, f prime is going to be negative, and then over here f prime is going to be positive again. So it's going to go like this. It's going to make a nice smooth connection about halfway in between. It's going to have a little hump there, and then it's going to come back. Okay. And then the graph is going to go on like this forever and ever. Okay. There would be this is the graph of f prime here. Okay, some things to notice. Notice that this is, you can see it's decreasing at a decreasing pace here. It's slowing down, now it's decreasing here. And then it's increasing at an increasing pace, and then it slows down to increasing at a decreasing pace. And then it's decreasing at an increasing pace, and then right about here it switches to decreasing at a decreasing pace. So it's anytime it's leveling off, anytime you can see the graph leveling off, like right here, you can see where that's happening. That means your derivative is getting closer and closer to zero. And that makes sense because our derivative is zero at that bottom or at this top up here. So there's the derivative, our sketch of our derivative. Alright? Now, let's look at the next one. Okay, this one, it does not appear to have any, it looks like this graph is increasing the entire time. It doesn't look like it's decreasing at all. So which means my derivative should be positive the entire time. It's never going to be negative because this graph is increasing the entire time. F prime is going to be positive the entire time. Now, we can tell a little more though because this is leveled off here. It looks like it would reach a minimum if we let it go this way. It looks like it would reach a minimum here, which means it's increasing rather slowly, and then it speeds up and then it levels off again. So anytime that it's leveling off, it should be getting close to zero. So my derivative should be pretty close to zero here. Okay? And then it, right about, you can see the end here, which is right about here. It should be back to being at zero, being close to zero. So it's going to go up, it's going to speed up, and then it's going to slow down, reach a maximum right about here, and then it's going to slow back down, and it's not quite going to get to zero, but it's going to get close, and that would be our derivative. You can see how this is rising slowly, speeding up, speeding up, speeding up, and then right about here it starts slowing down, how it's going to, and it levels off. So that's why this derivative at this point of change here, that's an inflection point, it changes that graph. Okay? Alright. Differentiable and continuous. This is an important idea. This is an important idea because if a function is differentiable, okay, at a, then the function is continuous at a. Now the converse of that is not true. In other words, just because a function is continuous doesn't mean that it's differentiable. But if a function is differentiable, it's automatically continuous at that point. Okay? How a function fails to be differentiable? Well, there's several scenarios here. One would be something you've seen, a corner. Something like this, an absolute value, that corner would not be differentiable there. Okay? If you have some kind of discontinuity, it can be any kind of discontinuity. If you have a jump like this, that would not be differentiable. Okay? A vertical asymptote would also make it not differentiable. Now, one more thing that doesn't happen quite as often, but it does happen, and that would be a function like this one, where it goes something like this, and it's very hard to draw, but if you had a point like this that had a vertical tangent, which does happen, but again, not that often. Not that often that happens. Alright. Sketching the graph of a piecewise function. Well, now we just take the slope, but we know that at these corners here, it's not differentiable, so our derivative would have to have empty circles there. So what we do is we say this one, it's decreasing, and if we take the slope there, it's going down 1 and right 1, so that's a slope of -1. So from -5 to -4, this has a slope of -1, and we put empty circles on the ends there. Okay. And then -4 to -3, that has a slope of 1. And again, we put empty circles there, empty circle there. And then from -3 to 1, it doesn't change. It's 0. The slope is 0. And from 1 all the way to 5, it's going down 1, 2, 3, 4 over 4. It's got a slope of -1 again. So from here all the way to 5. There is our drawn derivative. Okay, each little section of this piecewise function gets its own little section of derivative. Good.